The first technique we'll consider when trying to solve boundary value problems is a technique called the shooting method, and in actual fact this is usually the technique that you would choose to use for a boundary value problem. So let's go back and recall our previous problem where we had a projectile that we needed to find the barrel angle of that gives a range of 13,500 meters. So the blue curve here is the range of our projectile as a function of the barrel angle. We want the distance the projectile travels to be 13,500 meters. So how are we going to define this problem so that we can find those angles automatically using some kind of computer code? Well, let the range equal a function d of theta, that blue curve there. Let's define a new function, f of theta, and f of theta is simply equal to d of theta minus 13,500. So if we actually plot our new function f of theta, it's exactly the same as the old function, except we've just changed where the 0 is. We've just shifted that blue curve down, sorry. F of theta has two roots, one near 20 degrees and one near 50 degrees. So these two values of theta satisfy our condition that d of theta is equal to 13,500. So what we've done is we've converted our problem into a root finding problem. The question is, however, how do we calculate the function d of theta? And obviously we need d of theta in order to calculate f of theta. Well, d of theta is found by solving the ODE for a specified value of theta at the boundary. So we choose a value of theta and we integrate it. And we can do that for any value of theta, so therefore we can specify our function d of theta, which allows us to specify the function f of theta. So this process of using a root finding method to determine the correct value of a parameter to use in the solution of an ODE in order to satisfy a boundary condition is called the shooting method. Bit of a long, complex sentence, so it's probably worth your while spending a bit of time to make sure you understand it. Now, just as an aside here, theta doesn't appear explicitly in our equations here. It is actually associated with the initial velocity components Vx and Vy. But that's just an aside, and it's not going to be important for anything that we do. So let's have a look at the generic boundary value problem. Let's abstract what we were just doing with the projectile into a more general case. So let's consider an ODE over the domain x left to x right. And we're told that the solution must satisfy that y of x right is equal to some right-hand side value. We're just going to call that y RHS, y right-hand side. So we know that our solution has got to be equal to that when we get to the right-hand side. However, we are not given all the necessary information at the left-hand side. So, for example, we don't know what y of xl is, or perhaps the first derivative, or something else that's important to be able to solve this problem. Let's focus on the case where y of xl is the thing that we don't know. So what's y of xl here? We don't know what it is. So how could we tackle the problem? The first thing you might try is to say, well, let's make a guess. Let's choose y of xl is actually equal to y naught. So we choose a value down there, we solve the ODE, we get to the right hand side, and the value we predict at the right hand side is given by this red dot here, and we're going to call that yr for right hand side is a function of y naught. So if we put in y naught into our ODE and integrate, we get yr of y naught. Well, we could keep making guesses. Make a guess y1, integrate to the right hand side, we'll get a different value, yr of y1. Left hand side value of y2, integrate, we'll get another value, yr of y2. Choose a left hand value y3, integrate, get a value of yr of y3, and so on. We can do this for as many points as we wish. The value that we predict at the right hand side, yr, is a function of our left hand side guess. So in other words, we can write yr as a function of y left. Let's plot y right hand side as a function of our left hand side guess, and it's going to look something like this. And we can actually put a line through that if we like, and we can choose as many points as we like and make that function as detailed as we wish. So the correct value at the left hand side is found from the intersection of that green curve there with a straight line. Y is equal to y right hand side. Remember, this is the value that we're trying to aim for. So if YR is equal to y right hand side, then we've found the point that we're looking for, the value of y left that gives us that, and that's just that intersection point. So if we choose this value of y left hand side, we're going to get a value at the right hand side which exactly matches this value here. That's what we're seeking to do. So the function we need to find the root of in this case is written as f of yl, that's the function, is equal to yr of yl, remember that's the solution of the ODE at the right hand boundary, minus the right hand value that we're aiming to achieve. When these two things here are equal, then obviously this has got to be equal to 0, and we've found a root of this function. Now, if we know the range in which the root lies, then we could use the bisection or false position method in order to do this. Else, probably the secant method is the best option. Certainly, Newton-Raphson is not possible here because we have no idea how to write the actual function. Recall that our function is actually the solution of an ODE at the right-hand side point. So how do you write the derivative of that? It's not really possible. It's very important here to note, and we will see this in a minute. It's possible that the condition at the left-hand side is a condition on the derivative of y, not the value of y. Okay? This depends on the problem, and you can only determine this on a case-by-case basis by looking at the information you've been given for that particular problem. And we'll see examples in a minute. So, let's have a recap of the shooting method outline. So first of all, we need to determine which boundary conditions have to be satisfied and determine what values they have. Next, we need to identify what the adjustable parameter is, and we'll just call it k for simplicity here, but it might be a function value or a derivative value. We need to jump-start the root finding problem, so let's say solve the equation for a couple of different values of the parameter ki. That then allows you to determine a few different values of f of ki. Then perform root finding on this function, f of k, which is yr of k minus y right-hand side. Once we have solved this root finding problem, we will have the value of k that gives us f of k is equal to 0, or y right-hand side of k is equal to the right-hand side value that we want. So when we found the correct value of k. Once we have found that correct value of k, we solve the ODE using that to obtain the final solution for y of x. We'll go through some examples in subsequent videos.